Associate Professor of Electrical and Computer Engineering. Michael came to us just recently from the University of Arizona, where he's been recently appointed to Associate Professor of Electrical Engineering there. But he's actually coming home because he started here. He actually started at WashU in St. Louis. He got an undergraduate degree in mechanical engineering from WashU. Came to Duke and received his master's degree and PhD from the physics department, where he was doing thesis work on quantum degenerate gases. Then he did a postdoc here with David Brady's group, got into this area that he's going to talk to us about today, computational sensing, and then moved on to the University of Arizona, where he was assistant professor rising to associate and growing his work on computational sensing. I think you're in for a real treat today. He's a great researcher and a great communicator, which is going to make it fun for all of us. Please welcome Michael Gehm.
Thank you. It's a real pleasure to be here and be able to talk to you. I'm going to apologize. I'm getting over a cold. I'm going to really rely on the microphone because if I have to project, I won't be speaking by the end. All right. So my talk today is titled "Taking the Measure of Measurement: Understanding Modern Approaches to Sensing." I actually struggled a lot when I was trying to come up with a title. I was dithering back and forth between two. The alternative was getting a sense for sensing, understanding modern approaches to measurement. And wordplay aside, those titles were actually important to me because, and here I can only speak for myself, but when I think about a phrase like getting a sense of something or taking the measure of something, it actually seems completely divorced in my mind, unless I explicitly think about it, from the actual literal meaning of the words, of making a measurement or sensing something. And other phrases, having a feeling for something or someone's taste in clothes, all these things, again, at least in my mind, I think we blur the distinction between what they mean and the fact that they all refer to knowing something. And so the process of measuring or sensing and knowing kind of blur together in our minds. And I don't know if this is because, I suspect it's almost a familiarity breeds contempt. I mean, if we think about sort of the three branches of information science, we have computation where we process information, and we have communication where we transmit information. But the only way that we ever get new information about the physical world is by making a measurement or by sensing, either with our physical senses or through some instrumentation. And so, you know, we're so used to filtering all of our experiences through our senses that sometimes it blurs the line between the process and the result. And this actually speaks to a subtext in the first part of my talk that I'll get to. So today's approach to the talk, I actually work in several different areas, but I consider computational sensing, as Tom mentioned, is my primary focus. Computational sensing is very strongly represented in the ECE department, also in math and statistics here at Duke. In fact, that's what brought me back. In my opinion, there's no place else in the world that is more the center of work in that area. But maybe the ideas aren't broadly spread across Pratt. And so after talking with the dean, I really saw today as an opportunity to reach out to faculty and students and potential collaborators in some of the other departments. I could spend the time just going from result to result to result, but this would really focus on specific modalities and specific pieces of equipment that we had built and maybe obscure sort of more the general approach and the theme, which can be applied to measurement in all its guises. And so the idea is that instead the majority of my talk is really going to be more of a conversational piece, trying to sketch and provide insight onto what I see are the sort of key pieces of computational sensing, and then close with an actual single example of my research. So whenever I'm at a cocktail party and somebody says, computational sensing, what is that? I say it's the math of measurement. And this is a great aphorism, right? It's pithy. It sounds great. It's got the good alliteration. But like all aphorisms, after you think about it for a little bit, you realize, what does it really mean, right? I mean, because what on earth does that mean? I mean, really, isn't measurement just counting, right? How much interesting math can there be? And sometimes measurement is counting, but I would claim that rarely is it counting. It really depends on the question that and the specific thing that you're asking about. So for example, how much is that worth? This is sort of the canonical example. We have discrete quanta of value there, right? This is as much as measurement ever gets to be counting, all right? But same question, that one's maybe, there's a wrinkle. Okay, fine, but fine. So that's a judgment call. What about this? Well, so now we have a continuous object and we have a discrete scale. So that's a wrinkle, and let alone the bit, from chem lab. Oh, you got to measure on the bottom of the meniscus. There's all this kind of stuff. So maybe that's not quite counting. Now we got this. Okay, this brings up two things. Maybe so. First of all, we have the potential issue that what we're trying to measure may be changing on a time scale that's different than our measuring device can respond on. Certainly a big deal in optics, especially in the visible range. And we also maybe have the issue of noise, right? So maybe our instrument itself introduces noise. And that doesn't even go into the quantum folks, right, where except in special circumstances, when they make a measurement, it actually changes the thing they're measuring. So we're clearly divorced from just simple counting at this point. And then we have this. What kind of plane is that? That's not even a quantity, right? Does it even qualify as a measurement? I mean, it's not a number. It's not specifically quantitative. It's an inference from numbers, the pixel values in the picture. So it's common, and there are whole departments elsewhere on campus that will spend time drawing diagrams like this to say that these are different, that we have measurement at the bottom, and then we build up all these different layers of experience and wisdom and knowledge, and that's inference. But my claim to you is that it's really all inference. Everything that you think of as basic measurement is actually an inference problem. It's just that most measurement devices obscure this fact by design. And that's really sort of the familiarity breeds contempt thing from the title, that you're so used to that you sort of have the two concepts have become entangled in your mind. So most traditional sensors, we would say, are isomorphic from the Greek, meaning equal shape. And what we mean by that is that the answer is just an ordered arrangement of the measurements. So if we have a picture here, the Golden Gate Bridge, or a scene, so we're in San Francisco, we're looking out at the bay, and we measure it, in this case, in the context of a camera with some discrete grid of pixels. Well, if we just take the pixel values and we just arrange them in the same order that they were arranged on the detector array, we get basically our answer, what was out there. Okay, now, true, we can do all kinds of image processing and post-processing. If we've paid attention in class, we're using sync filters and all this kind of stuff to properly integrate this up into a result. But nonetheless, the key step is simply just arranging the samples that we made in the proper order, and we get very close to the answer. So the whole point is that makes the inference step, going from the samples to the answer, trivial, and trivial to the point that you generally have stopped even noticing that step is there. And then you start to believe that the samples are the answer. So in the isomorphic approach, and we might call it the traditional approach, in any measurement device, the performance improves when you go to finer sampling. So if we use pixels that are twice as small, we get a higher fidelity representation of the scene. And this is what drives the desire in conventional sensor engineering, we might say, for smaller pixels, or faster analog to digital converters, or narrower optical point spread functions, and so on and so on and so on in traditional sensor systems. So isomorphic sensing makes this inference step trivial, but it constrains the available design space. So if we consider wow, that was quite the squeak. If we consider all the possible electromagnetic elements that could possibly exist, only a small subset, the class that we call lenses, facilitate isomorphic sensing. So there's a huge variety of potential components and systems and solutions that we have rejected a priori because we were insisting that the answers had to look like the samples that we made. Now, some of you have seen me use this slide before. The past 50 years, there's been a really huge change in the resource environment available to sensors. I'm going to highlight the optical domain because that's the primary area I work in, but a similar story can be told pretty much across the board. In the 17th century, processing was the biological human brain. Detection, biological human eye, and if you wanted to store an image, you had to get out the easel and begin sketching. In the 19th century, around the time of the Civil War, we get photographic emulsions, and that serves both as a detection medium and as a storage medium. But of course, it was after World War II that we get the full explosion. So we get electronic computation, for, starting with the earliest tube systems all the way up to modern processors. We get electronic detection, CCDs, all the way up to the cell phone scale CMOS arrays now, and storage. Magnetic tapes, magnetic disks, now flash storage, incredibly high density. It's just a completely different resource environment, but again, in the optical context, the basic optical sensor architectures, the camera, the spectrometer, were developed for this resource environment. And again, the way they were designed the way they were because the only inference problem anybody could solve was a trivial one. You had to be able to look at the result and understand it, which is certainly not the case today. Today, we can handle much more complicated inference problems. So do we gain anything by making that step, by acknowledging that measurement is always about inference and reveling in it? So we get an expanded design space, and this does provide significant performance increases. It's not that hard. You've actually been doing computational sensing yourselves for years. All right, so start with a really silly example. Your job is to weigh Mr. Mittens. Now, I've given this example a million times, usually with a suitcase or a piece of paper. Nobody ever pays attention, and I put up a cat picture and give it a silly name, and all of a sudden that's all anybody ever wants to talk about after the talk. Your job, you have to measure it with a cheap bathroom scale. And this isn't one of these fancy strain gauge digital readout kind of stuff. We're talking, the stuff with hysteresis. It doesn't budge until you put 50 pounds on it. So what are you going to do? Well, I hope the answer is obvious to everybody. You weigh yourself, and you weigh yourself holding the cat, and the cat's weight is the difference of the two numbers. It's computational sensing. Let's look at it. You inferred his weight from the measurements, but the answer was not the measurement values. It's not isomorphic. That would have been weighing him directly, which you couldn't do, right? Adding the computational step provided a capability that wasn't available to you. The scale didn't respond to the cat. And to be clear, this is not traditional measurement followed by post-processing. You have changed the measurements that you have decided to make to bring this computational step into being. So mathematically, we tend to represent this idea of making measurements and computing the actions most generally as operators. So if we think about the thing in the world that we're trying to sense as some vector W, well, we just say there's an operator H, a measurement operator, and what it does is it turns this mathematical representation of the world into a set of values that we get as measurements M. And if we want to work backwards, well, we have a reconstruction operator which we can apply to the measurements and to get back an estimate of the source values. Okay, so it's not, we don't get back the exact thing, right? But we get back some estimate. And so the goal, in one sense, is to try and find this so that we get back an estimate which is as close as possible to W. That's at least one goal that we might have. Now, the operator was very general. We can be a little more specific, and we can say, well, in the context of simple, noisy linear measurement, we can say that operator H, what really is happening is we have a matrix T which transforms this description of the world, but then, and that gives sort of the ideal thing that we should measure, but then that's corrupted by some noise that comes about from the environment or what have you. And T is really the key to the whole story. It goes by, the community is not really settled on any specific name. It's the sampling matrix, measurement matrix, projection matrix, coding, or multiplexing. What it does is it describes the combinations that you're going to choose to measure. And so the way to read, so here's the measurement matrix for the problem with the cat. So the rows indicate different measurements that you're going to make, and the columns correspond to the different elements of the world. So the top one says, I'm going to weigh myself, 1, but not the cat, 0. So the first measurement is I step on the scale by myself. The second measurement has a 1 in both columns, which means the second measurement is both of us. Okay, so that's how that works. Now, isomorphic sensors, their entire concept is to work to make this as close as possible to the identity matrix. Okay, that's what is equivalent to measuring each thing in the world by itself with as high a fidelity as possible. Okay, so enough cats. It's Christmas time. So holiday packages are showing up on people's doorsteps. So we want to determine the weight of 4 parcels. Those weights might possibly be unique. Now we're really dusting off the old instruments here. We have a balance scale. It gives the weight difference between the 2 pans, right pan minus left pan, plus a small random error, those darn air currents. And we're going to say you can only use the scale 4 times. So if we use the simple noisy measurement model that we described, the question now becomes, what measurements should we choose to make? How do we design this measurement matrix T? And so we start by determining the constraints on T. And the constraints on T are fairly straightforward. T can only contain the elements of T can be only one of 3 things. It can be a +1, indicating we put that item on the right pan in this measurement. It can be a -1, indicating we put that package on the left pan in this measurement, or a 0, which says that package is not involved in the measurement in this particular measurement. There's no other constraints in this example. And then we also need to determine what reconstruction strategy we're going to use. You can show that if we're going to limit ourselves to linear methods, least squares turns out to be the right approach. And this is basically equivalent to saying that the reconstruction operator is just the inverse of the measurement matrix. And so if you just slam that through, what you end up seeing is that the estimate of the weights is the true value of the weights, but then we have an error factor which has this form, T inverse n. And so in the isomorphic case where T is the identity matrix, then T inverse is also the identity matrix. And so your estimate of the weights is corrupted by precisely the noise that was introduced into the measurement process. But if we can, the question then is, can we design T such that this term is smaller than n by itself? If so, we've reduced the error in our measurement. And so our measurement strategy is then, this is kind of the key step. We've gone from a physical process to now asking questions about the properties of a given mathematical object. And indeed, in case you're wondering, we can find a T that improves performance over the isomorphic approach for the conditions I described. It's a set of mathematical objects known as Hadamard matrices. Specifics aren't important, because each problem is different. But indeed, these kinds of problems are solvable. The key point, though, is that the result has to be consistent with the constraints imposed by physics, right? Which may limit how we interact with elements of the world, may interact with the types of values that we get from the world, the instrument architecture, which may limit not only the values that go in the matrix, but perhaps higher order structure in the matrix, as well as available reconstruction algorithms. So finding good solutions or mathematical objects that have good performance subject to these constraints is really what computational sensor design is then. So that's sort of insight number 1, realization number 1. Measurement is inference, all right? The sort of that whole section, we should embrace it. Modern systems can afford to solve more challenging inference problems. We do not have to limit ourselves to stuff that is immediately solvable by biology. And in doing so, we expand the design space, and it leads to increases in performance. OK, next piece. Sometimes we actually don't care about the values. We just care about what the values imply. What is that? Who is that? If I drink this, am I going to get sick or die? We can also, instead of focusing on the fidelity of the reconstruction, we can be focusing on performance on these tasks. So we can design sensors that are task-specific. They seek to address these questions directly. In this case, now we're giving up general purpose capability. We may no longer know what the values are. We only get answers to the specific thing that we're trying to determine. But in doing so, we can get increased performance on a specific task. So again, let's look at another toy example. 4 boxes again, but now we work for quality control, and our job is to determine if they all have the same weight. Again, we're going to use the balance scale. So we could just use the strategy we did before. It told us how to, I didn't go into the details, but if we use the Hadamard matrices, we could measure, we would know how to make the measurements to get the best estimates of the box's weights, and then we could compare those numbers, and that would work perfectly well. But we could also make these three weighings. If the scale balances on all three, then all four boxes have the same weight. So there's two advantages that this task-specific example has brought to bear. We have to make one less weighing, and we don't need a numerical readout. Remember before, it depended, we were going to have to process based on weight of the right pan minus the left pan. Now we just need to know, does the scale balance, okay? So we've simplified what we have to do, and we've simplified our instrument by needing to only focus on an answer instead of trying to get the values of the boxes. And so, of course, the task can really be viewed as being about relationships, right? If it turns out if all three of those relationships, boxes' weights are equal, then by transitive properties, they're all equal in weight. And so we have three things, and we make three measurements. So that's realization two. Your task can matter. Okay. Next two pieces get a little more challenging, I think. At UA, I taught a graduate course on, it was called linear system theory, but it was basically abstract linear algebra and functional analysis. And there was always a theorem in there that I loved teaching because it was so central to what I did with measurement. So we frequently consider the underlying state of the world as being one of many vectors in some high-dimensional vector space. And we can imagine that we have a rule, specifically called a type of rule called a linear functional, that says how any vector gets mapped to a number. So we have a rule, and if we apply it to the red vector, we get the value A, and same rule applied to the orange vector, we get B, and it's linear. So if we have a linear combination of vectors, we get a linear combination of the answers. This is essentially how we want measurement processes to behave. Okay? First of all, it's a mapping from a state to a number, and measurement any sampling ultimately results in a quantitative value. And the linearity is more our comfort level. We like things that are linear. We can understand things that are linear. This is actually a key point that, what I'm going to tell you all depends on it being linear, which means considering what happens when we have nonlinear mappings to values and how nonlinear measurement works is also a very interesting academic path to go down, but is not one I'm going to talk about today. So for many things, let's say, this is an exceptionally accurate representation of what we mean by of how sampling should behave. Well, it turns out the theorem says that given any such rule, doesn't matter what it is, as long as it maps vectors to numbers and does so linearly, you can find another vector in the space such that if you project any one of these vectors onto that vector, you get the same numerical value as if you applied the rule. So if we say our rule, we go through the process and it says, okay, the corresponding vector is this green vector. And remember, here's sort of, how the rule behaved. What we're saying is once we've found this green vector, if we project the red vector down onto it, this distance here has length A. And if we project the orange vector down onto the green vector, this distance right here has the length B. And that's true for any of the vectors in the vector space and any linear combination of vectors in the vector space. And we can introduce sort of this bracket notation that will look familiar to some people to represent this projection. And then the linear combination piece works like that in that notation. So any linear measurement process can be viewed as a projection of the underlying state down onto another vector to get a single value. And further, if we have a set of measurements, okay, if we're going to take the vector and we're going to project it onto one vector first and then onto another one to make a different measurement, right? We have different measurement rules that we're going to apply. We're going to get a list of numbers. Well, it turns out we can think of that list of numbers as being a vector, and that vector is the vector that you get if you simply project your original vector into the subspace that spanned, right, in which these all the set of projection vectors live. And so we can not only limit ourselves to thinking about it as projection to a number, but we can also think about it as projecting from a vector in one vector space down to a vector in a lower dimensional vector space. So this brings up what I hope is an obvious point. So the results of the projections, right, depend on the length of the state vectors and the angle that they make with respect to the vector we're projecting onto. But if we're looking at the difference in the results and fundamentally our ability to in any way distinguish between these different states of the world depends on the relative lengths, right, how much longer this one is than this, and the angles between them. So really it's our ability to do anything and to say anything doesn't depend so much on the specific projection vectors we use. There are some that are better than others, but fundamentally, our ability to say anything about it actually comes down to the geometry of the set of state vectors that we're dealing with. Okay, so realization insight number 3, measurement is projection. All right, but there's a wrinkle. Our experience with projections in low-dimensional spaces leads us astray when we have to deal with projections, i.e. measurement, in these high-dimensional things. And essentially, measurement tends to occur in spaces of very high dimension. So if we think of like a megapixel image, we can think of that as a vector in 1,000,000 dimensions. And as we know, David's got a gigapixel, so there's 1,000,000,000 dimensions, right? I mean, so time sequences, any type of measurement tends to be in what, for us as physical beings, are extremely high-dimensional spaces. All right. So again, our intuition is not so great in high dimensions, and so this is how I like to intuitively understand this problem. None of this is rigorous, but some of you may be familiar with the fact that in high dimensional spaces, the vast majority of an object's volume comes from the periphery. And so this graph will take a little bit to explain. So here, what I'm doing is I'm looking at hyperspheres, balls that are of some dimension, ranging from 1 dimension all the way out to 1,000,000 dimensions on a logarithmic scale there. And I'm computing how much of that ball's volume occurs within a thin shell on the outside that's 5% of the full radius, 1% of the full radius, 0.1% of the full radius, and 1/100th of a percent of the full radius. So what we see, and I'm sorry the numbers are so small, is that basically if we're willing to, that essentially all of the, this is 100%, this top of the graph. So essentially 100% of the volume of a hypersphere occurs within 5% of its surface when you're in about 30 dimensions of 30. If you want to limit yourself to the outer 1%, then it's about 300. If you want to limit yourself to the outer 0.1%, you've essentially got all the volume after about 3,000. And if you want to limit yourself to the outer 1/100th of 1%, you essentially have all the volume living there by the time you're at about 30,000 dimensions. And again, those are relatively small dimension numbers for the kinds of things that we deal with in sensing and measurement. So essentially, we're always dealing with these very high-dimensional spaces where almost all of the points live near the periphery of the object. And so in the volume, we can kind of think as, again, in a very hand-waving sense of indicating where the majority of available points in this space occurs. So what's the point of all this? All right, this is probably the trickiest thing for me to explain in the whole thing. Projection into a subspace. Remember, we said when we're going to measure, make a sequence of measurements, we can think of it as projecting the state vector into a subspace. At best, that can maintain the length of the state vector. Almost all projections result in the vector becoming shorter. Now, I'm limited because I have a 2-dimensional screen up here. So if my initial space here is 2-dimensional, the only available lower dimensional subspace for me to really work in is 1-dimensional, which is lines. So I want to consider this initial red vector as I project it into different 1-dimensional subspaces, which are lines passing through the origin. If I project into the subspace that exactly aligns with the vector's length doesn't change. If I happen to project into the linear subspace that's perpendicular to my original vector, its length goes to 0. Anything in between, and the projection is shorter than the original vector. And if I continue around in all the other quadrants, all that happens is I pick up sign changes, but I don't change the length. So basically, I'm stuck with keeping the vector's length the same length or shorter. Now, the possible result of any projection has to then terminate within a sphere which is of radius equal to the length of the original vector, right? Because I said, that's the set of all points that lie within that distance of the origin. But you just saw that if the subspace I'm projecting into, so now way beyond what I'm able to sketch up here, but if the projected subspace is still a very high dimension, then the vast majority of possible outcomes occur essentially at the surface, which means that the length of the vector is effectively unchanged upon projection. Okay, it's approximately maintained with very high probability. So now, we can think about two of our original state vectors, which the red and the orange, which I'll call A and B. We can also define their difference, A minus B, which is also a valid vector. And this creates a triangle. Well, if the lengths of the sides of the triangle are approximately maintained, you think about it from similar triangle perspective or law of cosines or law of sines, it means the angles are also approximately maintained. And specifically, this angle is approximately maintained. But earlier we made the point that the overall geometry of the state vectors was fundamentally the relevant piece. And so what this shows is that that geometry survives projection to a lower space as long as the ending space is still of a high enough dimension. So this is completely different than our intuition in lower dimensions. When we start with an object of a cube and we look at its shadow, it gets very distorted. If we look at a drawing of a box and we project onto a line, it gets very distorted. What happens is the underlying geometry of these objects, as long as we terminate in a sufficiently high enough dimensional space, actually is not affected to any major degree with reasonably high probability, which is, again, very different than our intuition. So what this means fundamentally is that the outcome of a relatively small number, again, it has to be large in terms of the ending dimension, but it can be small compared to the dimension we started in. A small number of measurements contains approximately the same information as the original state description, which means that we can extract results of a given fidelity without taking the corresponding number of samples. Oh, and I skipped. So that's basically a completely hand-wavy description of something known as the Johnson-Lindenstrauss lemma, which really energized people since the mid-'80s to really thinking about what this means for measurement, and that's fundamentally what it means. And in really the last decade, there's been very rigorous and intuitive exploration by many groups in the subfield of compressed sensing, and which was essentially the essence of Galen's talk in this series earlier in the year. Okay, so realization 4 is that high-dimensional spaces are weird. We don't intuitively grasp them because we are fundamentally low-dimensional beings, but that they are wonderful and they provide a amazing capability that we can bring to bear in certain aspects of sensing. All right, so that's kind of the end of the conversational piece. It's again, I can't teach you how to do computational sensing, but I can hopefully convey to you sort of the kinds of thoughts and considerations that we apply regardless of the sensing domain, the measurement domain that we might want to consider, and sort of the opportunities that they provide. So with the remainder of my time, I want to take a few minutes to look at a specific application from my group, which is in the context of adaptive spectral imaging systems. All right, so again, this may not be an area that you're familiar with. So spectroscopy, right, is looking at how much electromagnetic power you're receiving as a function of frequency or wavelength. And it's valuable as a sensing modality because it details about matter that is interacted with that light or imposed onto this electromagnetic spectrum. Typical spectrometers probably work within the order of hundreds to thousands of signal elements. So if we think about a typical spectrum, we think about it as a vector living in spaces of hundreds to thousands of dimensions. Spectral imaging is a generalization of spectroscopy and imaging. Basically, what we do is we have an array of spatial locations, and now we take a spectrum at each one. So you can think of it as like a color photograph, but instead of red, green, blue, we have hundreds or thousands of signal channels, so we have a full spectrum at each location in the scene. Or you can think of it as spectroscopy done at every position in a scene. So you tend to have about 100,000 to about 1 billion signal elements in a spectral imaging. So 100,000 to a billion dimensions. So again, very, very high dimensional stuff. So the central idea of the instrument I'm going to talk about is that rather than capturing spectral data, and then performing exploitation, trying to say classify what it is, what compounds we're looking at via post-processing, what if we design the instrument to directly perform this task? And what do we do and what if we allow it to be adaptive? That's a wrinkle I haven't talked about. The upshot is that we see multiple of order of magnitude gains in performance. So let's pause for a minute. So this is going to be, we're buying completely into the inference idea. Okay, so this is going to have complicated inference problem. It's going to work via, it's task specific. We're going to be doing classification. It's going to work via projections in very high dimensional spaces. So it's compressive. So everything we've talked about, in addition, a key idea which I didn't discuss in the conversational piece is something that's being investigated a lot more in computational sensing is what if you allow the system to respond to measurements it's already made, so it can become even more powerful. Basically, you continually perform the design process on the fly as you're gaining information. So this system really brings really uses all the different aspects of what we've been talking about up till now. So spectral classification. So usually, unlike pretty pictures which people take and stick in a drawer or on their hard drive, nobody really ever takes a spectrum, a pretty spectrum, right? So the spectra are usually not the goal. Usually there's some task in mind. And classification is a very common one. And what we mean by that is basically you have a measurement and you want to match it to a library and you want to say, oh, it's that thing. All right, so we can consider our library in this form. So these are the spectra as a function of wavelength or frequency band or what have you. And there are three there, and then there's actually a measurement that's been imposed on top of one of them. We can think of our library, again, as these vectors that live in this high dimensional space. And we want to know which one is present at our instrument. But of course, our instrument isn't perfect. There's noise, and so what we're going to see is not if we measure where we are in space, we're not going to measure the precise tip of the vector. We're going to measure somewhere within like a little bubble around it, and so when the noise is small and you can't even really see the fuzz that I've put on one of the measurements here. Basically, you end up with these noise balls that are very well separated, and you see which one it falls in, and classification's easy. You say, oh, it's in that one. It's the compound that is the green vector. But as noise increases, then what happens is these noise bubbles in this vector space concept start to overlap. So if now you make a measurement and you see a point that exists kind of in this overlap region, you've got this ambiguity. Did I see, is it the green one there and the noise kicked me this way, or is it the red one there and it kicked me this way? And then as the noise increases, you can get it so that the noise bubbles are really all there is, and they just overlap. So we need to have a concept of how hard it is to do a classification. So we can define something that we call task SNR. And basically, in all of these, sort of the key idea is we want the separation for an easy problem. The separation between the tips of the vectors should be large compared to the size of the bubble. And so that's what this measures. It measures the minimum separation in the set of vectors that we're considering in our library in units of the size of the bubble, and then we just convert it into dB. And so just to put numbers with it, we would say this problem, which is trivial, is a 25 dB task SNR. To this one, which looks very hard, is minus 25. Right? 0 dB would be when the noise bubble is essentially the same size as the separation of the things in the library that we're trying to distinguish. All right, so for the instrument that we've built, we're using an optical architecture that we call Dual-disperser. The details aren't too important. It's basically two dispersive spectrometers back to back, one which spreads the light out, and then it falls on an active device, a digital mirror device. It contains a little over 1 million micron scale mirrors, which are individually controllable and can affect the light, and then a second arm which then puts that all back together. And the net effect is, so we start with sort of light that comes in, and the light there's two spatial dimensions and a spectral dimension. It gets smeared by its interaction with this first dispersive element, and then this mirror thing can punch these weird kinds of holes through it. The second dispersive element straightens it back up. So now spatial locations are back sort of where they started. And then the detector loses all spectral information. The guts of this aren't important, but what's essentially happening is the measurement that we're getting at each spatial location is the projection of the spectrum that was there with a filter function which we can control on each spatial location. So this is the projection piece. We are able, by suitably designing the pattern of mirrors here, to design the filters that each spectrum is projected onto. And so our detectors elements now measure the values of these projections. And again, measurement is projection. So we call these projections, sometimes people call them features. What we want to do is, so the conventional computational sensor design would design those projections, and we want to design them to be as good as possible. The wrinkle here is we want that design to change as we learn stuff. Okay, and so it turns out that what is the optimal projection direction only exists if there's only two things you're trying to decide between. As you're trying to decide between more possible compounds, we have to have some other way of designing the vectors. We use something based on principal component analysis. Again, the guts of it aren't important, but the idea is if you think of these dots as the different compounds, if we start out by projecting onto a feature which is described by this vector, then that gives us relatively good separation. So for example, this dot would project to this location. This dot would project to this location. So unless we had a tremendous amount of noise, we could reasonably tell if we detected something down here that it didn't come from this compound. Okay? So that's the idea. But as we learn, we start to gain ideas about how likely the different dots are, the different compounds. And so if in our next measurement, maybe we've ruled out almost all of the ones, or maybe not ruled out, maybe that's too strong, but we think they're likely with very, very low probability. And the only ones that are really significant are the ones that are still dark here. Well, we don't want to use the same projection vector we did before because that was designed to be highly discriminating between the whole set of the library. But we've ruled out a bunch of options. What we want now is we want filters that are good at discriminating between the things that we think are still in the running. And so that might be this direction. And so we want to filter a projection filter that is projecting like this, so that now we get good separation between this compound and this compound, and these are all kind of spread out. And so we can do all this, and we can do it in sort of a Bayesian statistics framework to build up probability estimates of all the different compounds. And so when you do this, the instrument we call the Adaptive Feature-Specific Spectral Imaging Classifier, AFCC for short, and we can look at how likely we are to have classified a location incorrectly as a function of the number of measurements that we've made. And these curves are for just different TSNRs, and notice the highest TSNR, that is the best, easiest problem I'm considering, is 0 dB, which means that we're considering problems where the noise is the same size as the separation. This is a tremendously difficult problem for conventional approaches, and it's the easiest problem that we're willing to consider. And we see that in that case, the adaptive approach, the error probability drops to about 1 in 10,000 after only about 12 measurements. That's 7 errors out of 65,000 spatial locations. Obviously, as the noise gets worse, it becomes tougher and tougher to distinguish. But nonetheless, this is really, really cool performance. This is simulation. So does this make sense? You might have noticed that the curves go to these straight lines. Well, they're straight lines on a semi-log plot, which means exponential decay. And there are all kinds of error exponential theorems that predict this behavior when you're dealing with a two-class problem. So what this is saying is that by the time we've gotten into the straight line portion, we've ruled out all but 2 items. Basically, it's come down to 2 things, and the system is just trying to hammer on which of the 2 it is. So very quickly, we jettison most of the possible options, and we really focus in on the toughest piece of the problem. And that's really why the performance is so good. So here's more simulation at different TSNRs. But what I'm comparing now, again, I apologize for the size. These are different mechanisms by which you can run the system. So the solid curve, again, is the adaptive system based on sort of the design framework that I described. We can use static features and turn off adaptivity, and you get this curve here and this curve here. Or we can use random features. That's a big deal and a common thing to do in compressive sensing, and you get the other curve here. So we beat both of those approaches. So adaptivity helps, and the design of the features helps over random. And these other curves are the conventional ways that people do spectral imaging. And so we are the numbers just kind of get ridiculous. We are 8,300 times better than a whisk broom-based instrument would be. What is it? 3,800 times better than a tunable filter. So these are the conventional approaches. These two and this solid curve are sort of the computational sensor approaches. And then again, the solid curve is the adaptive with designed features, and that's by far the best. So we've built an instrument based on this. Here's a picture of it. So the layout's a little bit different than the sketch earlier, but it is still sort of the two dispersive spectrometers back to back with the micromirror array. You can see the micromirror array there in the back, and the two arms, and then up to the detector. And some preliminary experimental results. So this is all based on this design framework. We're using a slightly simplified problem at this point as we're trying to dial in the calibration. So we're just trying to decide between 4 compounds or 4 classes, and we're using a smaller field of view. It's only 64 by 64 locations, so about 4,000 spatial locations that we're trying to classify in parallel. Basically, what you can see is, so there's the truth, and my guys at Arizona are unwilling to rerun the experiment with a D at this point. After the first measurement, you can see already we've classified many of the locations correctly. By the 30th measurement, we're better than 99% accurate. We've classified correctly over 4,000 of the 4,096 spatial locations. And again, this is experimental. This part's not simulation, right? So there's all the normal pain and agony in trying to do this. And what we're working on now is trying to improve the calibration so that we can push the spatial resolution and the spectral resolution up to the design specifications. And that just becomes, it's experimentally a very challenging problem, because if we were going to do a direct kind of calibration, there's 8 million signal elements in the design thing. We can't go through and measure them one at a time to sort of calibrate the system. So calibration itself becomes an interesting measurement problem, and one that actually I hope is eventually amenable to attack via compressive sensing techniques, because calibration is nothing but a measurement problem itself, and ought to be attackable via the same kinds of things. So I think that's hitting my 45 minutes right on the nose. So with that, I will stop. The whirlwind tour of everything, and thank you for your attention, and address any questions you might have.
For that very nice talk, which almost elevates us from the level of engineering to philosophy. And maybe you think that the question of the tree falls in the forest and no one there to sense it.
Exactly.
Right?
Yeah.
Okay. Questions for Mike?
So could that be used as a new form of measurement to take like LiDAR measurements?
Yeah, so people definitely apply these kind of techniques, to all variety of things. There are certainly people who are looking at compressive LiDAR, so they're using, methods so that they don't have to scan all the spaces, or there's a million different ways that you can bring this to bear on essentially any kind of measurement problem. Again, philosophy, right? I mean, science and engineering, in my mind, it's quantitative, right? I mean, it's about making measurements. Fundamentally, is sort of that's what distinguishes it from other aspects of human endeavor, and pretty much all of it's amenable to attack by these kinds of techniques.
So you're assuming that all the measurements are taken under the same conditions?
I'm sorry?
All the measurements that you're taking are under the same conditions?
Which piece of the talk are you asking about?
Well, I guess maybe the last example, or in general, right?
Well, so the last one definitely has. I mean, there's calibration
noise, right?
involved. I'm sorry.
There is noise, and which changes, but
Sure. So the Bayesian inference that is happening, has knowledge about the magnitudes of noise that are representative of the system, and that's folded in, right? So you're not assuming that the measurement is truth. You're assuming, that with some certain level of confidence, given sort of what you know about the noise that's inherent in the various transducers and stuff, that this is probably this close to truth, and that's all baked into the Bayesian inference. And that can all be, again, folded into in a deeper way than than I was able to discuss into the design piece, right? So if you have shot noise, you do one kind of thing. If you have additive noise, you do one other kind of thing. If you have temporal drift, you can fold that in. I mean, the key is, the reason why it's not just math is that you have to be able to describe the physics that's going on and capture the physics accurately. Absolutely, if you misunderstand what's happening, then you will come to an incorrect inference.
Right. I guess going back to the and I'm not an expert in this area, but like going back to the LiDAR question, if you wanted to map some area, for example, right? It might make a difference if you're using your LiDAR from a certain location, then you move to the next location and take other measurements, right? So, or you can do the same similar example with cameras, for instance, right? So does this changing the location of your measurement, is this gonna? Well,
so there's aspects which are about your hardware, and that doesn't matter if I move my hardware from here to there, right? And so that's captured largely by calibration and by understanding, what I physically have. Certainly, if I'm using my LiDAR in a jungle and I'm using my LiDAR on a city street, I may get very different types of responses. And to the extent that I'm folding that knowledge into my design, then certainly that can impact the results. But again, I think Galen and some of the other people are actually more suited to answer this. Certainly, the priors about what you are looking at can be folded into the process, both the reconstruction process and the design process. You don't necessarily have to know, I'm looking at this piece of the jungle. You have to know maybe statistics about what jungle looks like, and statistics about what city looks like, and things like that. But those kinds of priors can absolutely be introduced both in the estimation and inference piece and in the design piece. Absolutely.
Any other questions? Maybe one last one, just to expand on the LiDAR application. I remember in Galen's talk when we were talking about compressive sensing, which is sort of like a subset of this computational sensing, mostly focused on the random part, I suppose. But there was a killer application to MRI where there's a high price to be paid, both financially and in terms of patient time and being in an MRI machine when the needle needs a megapixel image.
Right.
So what are some of the other areas where this would have a big payoff?
Sure.
Is it video on the internet, or where is it?
Well, so the compressive side of it, whether you're using random or not, is all about reducing resources, and so sort of its performance metric is reducing resources, and so anywhere you have an application that's resource starved is potentially can be attacked by this. I would say the broader aspect is considers many different metrics, and more often is considering performance. So as you're seeing, we can using the same scale object, the same cost, we can sort of push the yardstick farther. So anywhere that's striving for high fidelity or
you measure something and accuracy you could measure.
Exactly.
Okay, if there aren't any other questions, then let's thank Mike for a very stimulating talk.